Hello students, today we are going to discuss about the topic of analytic function and concept of residue. It belongs to the chapter of complex variables, which is a very important part. Every year we can expect 3 to 4 marks from this particular part. Okay, so electronics and communications, electrical, instrumentation, civil, mechanical. It is not there for civil engineering, it is not there for computer science. Okay, so for remaining streams we have this particular syllabus of complex variables. So each and every year we can get a question either from the concept of analytic function or from the concept of complex variables. So that makes it a very important and very simple topic to learn from complex variables. So we'll start first of all with the analytical function. So before understanding about an analytical function, let us see how the complex function look like. Generally, just like the real function, we can write the complex function as a function of z, the way we write x and f of x. Okay, so f of x is going to be the function of x. Similarly here, z is a complex number or a complex variable, so f of z is nothing but the function of the complex variable, which is z. So whenever we write a particular function, we write f of z versus z. So z is nothing but x plus I y. X is the real part and y is going to be the imaginary part of the complex number z. Right, so when you write an f of z, which is a function of z, it is also going to have a real part and the imaginary part. Generally, the textbook notation is that we write the real part of the complex function in terms of x and y, and the imaginary part also in terms of x and y. So f of z is equal to u of x comma y plus I into v of x comma y, where u is nothing but the real part of the complex function and v is imaginary part of the complex function. So that is how we represent a particular function, the complex function f of z. Now there is something like a single valued and multiple valued function. Now what is the meaning of a single valued function? So if you take the values of z and the values of f of z, so there is something like a one-to-one mapping between the of z and f of z. That is what we call as a single valued function. That for a particular value of z, there is only one single value of f of z that is available. Now why we are discussing this one? Because we have to define an analytical function. Now how are we going to define an analytical function? Analytical function is a single valued function. A single valued function f of z, which is defined and differentiable So what is an analytical function? Whenever we are discussing about the complex functions, the analytical function is defined as a single valued function which is defined and differentiable. There should be a value in that particular domain and it should also be a differentiable function in that particular domain that we have selected. Then we can say a particular function is analytic in that particular domain under consideration. It is not necessarily that it is going to be analytic everywhere, but in a particular domain that we have selected, if it is defined and differentiable at each and every point, that is what we call as a analytical function. And it's a very important part because in the examination, they will give a particular function, the complex function, and they will ask you whether the function is going to be analytic or not. And sometimes they will give you the real part of the complex function and they will ask you the imaginary part when the function is going to be analytic in nature. So that is how the questions are asked in the GATE examination based on this particular property of analytic. Now, how can we say a particular function is analytic or not? It is okay that the definition says that it is going to be defined and differentiable at each and every point. But how can we test that a particular function is going to be analytic or not? Okay, so we know about the differentiability continuity that we have learned in the calculus part that we are going to apply here, and we are going to generate two set of equations that we call as a Cauchy-Riemann equation. So when these equations are satisfied, When these Cauchy-Riemann equations are satisfied, we say that the function is automatically analytic in nature. So let us look at what is a Cauchy-Riemann equation. So Cauchy-Riemann equations is nothing but, first of all, let us consider a function f of z, which has a real part u of x comma y and the imaginary part v of x comma y. When you differentiate u with respect to the dot of x, it's a partial differentiation. It should be equal to the dot of the partial differentiation of v with respect to the dot of y. This is condition 1. The second condition is that the derivative of u with respect to the dot of y should be equal to minus of derivative of v with respect to the dot of x. So these two equations is what we call as a Cauchy-Riemann equation. The first one is that dou u by dou x is equal to dou v by dou y. The second one is dou u by dou y is equal to minus of dou v by dou x. So this is what we call as a Cauchy-Riemann equations. So if one of them is satisfied, is that going to be called analytic? No. Both of them have to be satisfied. Okay. So when these particular equations are satisfied, we say that the function is going to be analytic function. Okay. Let us take an example and try to solve the problem. So given function is f of z is equal to z plus 2z bar, we have to test whether this particular function is analytic or not. F of z is equal to z plus 2z bar. We have to test whether this particular function is analytic or not. So you can just pause the video and try to solve the problem. Okay. Solution is going to be something like this. So first of all, let me write z in terms of x, y. Z is nothing but x plus iy. So therefore, f of z is nothing but x plus iy plus 2 into x minus iy, which is equal to 3x minus iy. It is going to be 3x minus iy. So this is nothing but u, this is v. So u is equal to 3x, v is equal to minus y. So dou u by dou x, what is dou u by dou x? Dou u by dou x is equal to 3. Dou u by dou y is equal to 0. Dou v by dou x is equal to 0. Dou v by dou y is equal to minus 1. Dou u by dou x is 3. Dou v by dou y is minus 1 and the remaining are 0. Dou v by dou x is equal to 0. Dou u by dou y is also equal to 0. This is okay. That dou u by dou x, I mean to say that dou v by dou y is equal to minus of dou v by dou x is equal to 0. That is okay. But this part is not satisfied. So because this is not satisfied, we cannot call it as an analytic function. The function is non-analytic in nature. The function is non-analytic in nature. Now let us take the second question. Given f of z is equal to 1 by 2 ln of x square plus y square plus I tan inverse of px by y. Given the function is analytic, find the value of p. Right? F of z is equal to 1 by 2 ln of x square plus y square plus I tan inverse of px by y. Given the function is analytic, then what is the value of p? Okay, so because it is given the function is analytic, automatically the dou u by dou x is equal to the dou v by dou y. So let us find the value of dou u by dou x. So u is nothing but 1 by 2 ln of x square plus y square. Dou u by dou x is 1 by 2 into 1 by x square plus y square into 2x, which is equal to x by x square plus y square. What is dou v by dou y? Dou v by dou y is equal to the top tan inverse. V is nothing but, let me write V. V is nothing but tan inverse of px by y So dou v by dou y, when you are differentiating tan, it is going to be 1 by 1 plus, okay, px by y whole square into the derivative of this one with respect to y. Right? So the derivative of this one with respect to y is minus p divided by y square into x. So which, on simplifying, it is going to be equal to that of minus px divided by x square, I mean to say p square x square plus y square. Here you have dou v by dou x is equal to x divided by x square plus y square. Dou v by dou y is equal to that of minus px divided by p square x square plus y square. If you equate both of them, because according to the Cauchy-Riemann equation, both should be equal. So if I call it as 1 and this one as 2, if 1 is equal to 2, if 1 is equated to 2, then the value of p is equal to minus 1. Okay, so if you equate dou v by dou x is equal to, dou u by dou x is equal to dou v by dou y, then if you equate them, the value of p should be equal to minus 1. If p is equal to minus 1, this is going to be x divided by minus x whole square is nothing but x square plus y square. So the value of p is equal to minus 1. So let us solve some gate problems. It is given that f of z is analytic. The real part is given as u of x comma y is equal to 2xy. Then v of x comma y must be right, f of z is equal to u of x comma y plus I into v of x comma y is analytic. The real part is given as u of x comma y is equal to 2xy. Then v of x comma y must be dash. So the first option is x square plus y square plus k. Second option is x square minus y square plus k. Third one is minus x square plus y square plus k. The last one is minus x square minus y square plus k. We have to find the value of the imaginary part of the function. So good thing is that they have already given the real part, right? And it is also that it is analytic in nature. So using the Cauchy-Riemann equation, we can verify the options. So you can pause the video and try to solve the problem. Solution is something like this. Given u of x comma y is equal to 2xy, so dou u by dou x should be equal to dou v by dou y. What is the value if you differentiate with respect to the graph x? It is going to be equal to 2y. So given are the values of v, right? From the function, we are able to find the value of dou u by dou x, which is equal to 2y. Now we can verify which of them is equal to that of dou v by dou y. So here, dou v by dou y, if you differentiate this one, it is going to be 2y. So this passes the test. This is not going to pass the test because here you are going to get minus 2y. This is also going to pass the test. This is not going to pass the test. So we are able to eliminate two options. The second one is u of x comma y, which was given. We can find the value of dou u by dou y, which is equal to the top. What is the value of dou u by dou y? Dou u by dou y is equal to 2x. Okay, dou u by dou y is equal to 2x. So this should be equal to the top minus of dou v by dou x. This should be equal to the top minus of dou v by dou x, which implies that the value of dou v by dou x should be equal to minus 2x. So which of them satisfies? Here dou v by dou x will be equal to 2x. This is not going to satisfy, and hence this has to be the answer. So the answer is option C. The answer is option C. So let us solve one more problem based on the same concept. So once again, it is based on the same model. Given the function f of z is analytic, which is u of x comma y plus I into v of x comma y. Given u of x comma y, what is the value of v of x comma y? So I think you can easily solve the problem. U of x comma y is e power minus y cos x. So dou u by dou x is equal to dou v by dou y should be equal to the dou of, okay, differentiation of u with respect to the dou of x is equal to the dou of minus of e power minus y sin x. Now what you have to do is that given the options, the values of v are given, right? So what you have to do here, you have to differentiate this one with respect to the dou of y, and you have to see whether it is equal to this one or not. The first one, if you differentiate with respect to the dou of y, you're going to get the same e power y cos x, which is wrong. This one, if you differentiate, you're going to get minus of e power minus y sin x, which is correct. This will not be the case. This one, if you differentiate, you're going to get minus of e power minus y cos x. This is not the case. So there is only one option that is going to satisfy, which is option B. So we have learned about the analytical function. Now let us consider the same domain where the function is generally expected to be analytic in nature. Let the domain name is T. Now if the function is analytic at each and every point inside this particular domain, on the border and also inside, if the function is analytic except some points, and those points are what we call as the singular points, indicates that expect these 2 points, except those points, at each and every point the function is analytic in nature. So the places or the points where the function ceases to be analytic in nature is what we call as the singular points. So for example, if I can take an example, f of z is equal to z minus 1 divided by z square plus 1. This function is going to be analytic each and every point except the denominator equal to 0. So z square plus 1 equal to 0, z is equal to plus or minus I. Now what happens at this particular point of z is equal to plus or minus I? If you put z is equal to I, the denominator is equal to 0, which is an undefined value. And we know that an analytical function is one which is going to be defined and differentiable in a particular domain that we have considered. When you put the value, it is going to be undefined. So have to make sure that the denominator is not equal to 0, because straight away when the denominator is equal to 0, it is going to lead to a non-analytic function. So the points where the function ceases to be analytic is what we call as the singular points. So these points are what we call as the singular points. So now let us step into the next topic, which is the concept of residues. You have to understand in the complex function, consider a particular function f of z which is analytic in nature. If the function f of z is analytic in nature, the domain that is considered is nothing but a circle. Okay. Now, if you want to integrate, if this particular circle is the contour that we are considering, so if you want to integrate the function f of z in this contour, if the function is analytic in nature, do you know the value of the integration here? What are we doing? Considering an analytical function which is going to be analytic at each and every point inside and on the contour that we are considering C. Now when you are integrating f of z around this particular contour, the value is equal to the dou of 0, which is what we call as the Cauchy's theorem. So very important theorem, many times the questions have been asked based on this particular theorem, that in a particular domain that we have considered, okay, which is written as contour C here. Now if the function is analytic at each and every point, there is no singular point at all, at any point inside or on the particular contour C, then if you are integrating the function f of z in that contour, the value is equal to 0. This is what we shall say it is a Cauchy's theorem. Now if you have any singular points, now you cannot assure that value is going to be equal to 0. We can say more often than not the value is not equal to 0. The function may not be equal to 0. That is because of the presence of these points. And because of these particular points, which are nothing but the singular points, this value is not equal to 0. This is what we call as the residue points. Okay? Because of the singularities, it is going to create a non-zero value, which we call it as a concept of residue. So we say that if this particular point is z1 and this point is going to be z2, then I can say that this value is equal to, instead of saying not equal to 0, I will say that this is equal to the residue at z1 plus residue at z multiplied by that of, okay, 2 pi multiplied by. So always this is going to satisfy that whenever you're going to have a singular points inside this particular domain, then the value of the integration is equal to that of 2 pi I multiplied by residue at z1 plus residue at z2. It's a very, very important concept because every alternative year you can find a particular question on this particular concept. Now how to calculate the residue? So let us try to find the residue at z1. Residue at z1 is going to be given by limit z tends to z1, okay, 1 by n minus 1 factorial. Please don't get frightened by the formula. I'll tell you how to memorize it. Okay, d power n minus 1 divided by dz power n minus 1 into z minus z power z1 whole power n into f of z. Okay, the residue at z1 is going to be equal to that of 1 by n minus 1 factorial, limit z tends to z1. Okay, the n minus 1th derivative with respect to z of z minus z1 whole power n into f of z. Now what is n here? We know what is z1. Z1 is a particular point where you are having a pole, right? Z1 is a point where we are having a pole or a singularity. Okay, pole is one of the form of singularity. There are different types of singularities. Pole is one of the form of the singularities. So z1 is that particular singularity, and n is nothing but number of times the singularity is repeating at that particular point of z1. For example, there are 10 singularities at the same point of z1. There is not one, there are 10 singularities at that particular point. Then the value of n is going to be equal to 10. So n is nothing but it is going to represent number of singularities or poles at z is equal to z1. Now if the number of singularities is equal to 1, if you are having only one pole at that particular point of z1, then the formula is going to be rather simple because n is equal to 1, 0 factorial is 1. Now there will not be any derivative, so directly the formula is going to be something like this. When n is equal to 1, for n equal to 1, then the formula is going to be very simple. Limit z tends to z1, z minus z1 into f of z. So whenever you have number of points, repeated number of singularities at a particular point, there are repeated number of singularities at a particular point. In such a case, you should have this particular formula, which is nothing but 1 by n minus 1 factorial, limit z tends to z1, n minus 1 the derivative of z minus z1 whole power n into f of z. The value of n is equal to 1. The formula is rather simple. It's going to be limit z tends to z1, z minus z1 into f of z. Okay, so the same will happen at z2 also. The formula, only thing is that in the place of z1 you will write z2. So f of z is given as equal to 1 minus 2z divided by z into z minus 1 into z minus 2. What we have to do is that we have to find residue of f of z at z is equal to 0. You have to find the residue of f of z at z is equal to 0. So you can see that at z is equal to 0, there is only one pole that is available. Okay, when you equate the denominator equal to 0, you're going to get the singularities. That is what we have discussed already. Now at z is equal to 0, there is only one. If there is z square, then there are two singularities at the same point, z is equal to 0. So whenever you're having a single singularity, then the formula is residue at z is equal to 0 is given by limit z tends to 0, z into f of z. So z into 1 minus 2z divided by z, z minus 1, z minus 2, limit z tends to 0, z will get cancelled, the remaining is going to be 1 minus 2 into 0 divided by minus 1 into minus 2. So which is 1 by 2. So the residue at z is equal to 0 is 1 by 2. Can you find the residue at z is equal to 1? What is the residue at z is equal to 1? Is limit z tends to 1, z minus 1 into f of z. So which is given by z minus 1 into the function 1 minus 2z divided by z into z minus 1 into z minus 2. Limit z tends to 1. So z tends to 1. Z minus 1 will get cancelled. So we will have 1 minus 2 into minus 1. I mean to say plus 1. So 1 into 1 minus 2, which is nothing but equal to of minus 1 divided by minus 1, which is equal to 1. Okay. Similarly, you can find the residue at z is equal to 2 also. Limit z tends to 2, z minus 2 into f of z. So what is going to be the answer? Limit z tends to 2, directly I am writing it as 1 minus 2z divided by z into z minus 1. If you put the value of 2, you will have 1 minus 2 into 2 divided by 2 into 2 minus 1. So it is going to be minus 3 divided by 2. So at residue at z is equal to 0 is 1 by 2, residue at z is equal to 1 is 1, residue at z is equal to 2 is minus 3 by 2. So let us take the next example. F of z is equal to 1 by z into z plus 2 whole cube, and we have to find residue at z is equal to minus 2. So we have to find the residue at z is equal to minus 2. So you can try to pause the video and solve the problem. Now let us try to solve this one. See, at z is equal to minus 2, yes, we have a singularity, but the number of singularities that are available at z is equal to minus 2 are 3. So the value of n is equal to 3. So the general formula that we have to apply is 1 by n minus 1 factorial into limit z tends to minus 2 d power n minus 1 divided by dz power n minus 1 into z plus 2 whole power n into f of z. So what is the value of n here? N is equal to 3. So we can directly apply, and the value of z1 is equal to minus 2. Okay, that I have already applied. So 1 by 2 factorial, limit z tends to minus 2. So d square divided by dz square, z minus 2 whole cube into f of z is nothing but 1 by z into z minus 2, I mean to say z plus 2, right? Z plus 2 whole cube. So z plus 2 will get cancelled here. So you will have the second derivative of 1 by z. So what is the first derivative? It is going to be minus 1 by z square. Second derivative is going to be 2 divided by z cube. So 1 by 2, which is nothing but 1 by 2 factorial, limit z tends to 2. So 2 by z cube, which is equal to 1 by 2 and 2 will get cancelled. We will have the value equal to 1 by 8. So the answer is that the residue is equal to the of 1 by 8. Okay. So this is the concept of residue. So many times the question has been asked. We have solved some problems on residue and also the problems on analytical function. Now apart from that, we have some concepts like the basic complex numbers. So we know that in the complex numbers we can represent a complex number in different forms, a polar form or a rectangular form. So we have used here a the rectangular form, I mean. So the questions have been asked, of course, on an easier level based on the basic complex numbers. That is very important for the examination, because sometimes the questions are asked which is very easy, which we didn't cover in this particular part, and also there is a formula called as a Cauchy integral formula which we didn't emphasize on this particular lecture. Okay, so this is for today. Okay, we have discussed about an analytical function, how to test an analytical function. So if a particular real part is given, how to find the imaginary part, and also the concept of residue. So that is it for today. Thank you.